Okay, so first, I'll tell you how I found this paper. This paper is one of the papers that got a Best Paper Award at iClear this year. And I chose it because I thought it was a really interesting combination of things. Like basically they kind of take this field of game theory and connect it to the field of stochastic optimization such that we can find solutions to games that we couldn't find before. And who knows to say how powerful that is. I mean, in the paper, they even make comparisons saying like, this is kind of like the beginning of ML in terms of neural networks. It's like we've figured out how to, it's like the equivalent of when they figured out that they could train good neural networks with stochastic gradient descent. So they're saying like maybe this blows open the field. Before going into the paper, one of the questions I wanted to answer for you guys was, where are Nash equilibria and normal form games used in application? And if I did a quick look online, by no means comprehensive. And I really actually didn't find many examples of Nash equilibrium being used in practice where there's like an actual computational element to it. So there's tons of examples in tons of different fields about like the conceptual idea of a Nash equilibrium, especially in like economics, behavioral theory, and they even say it here. I'll even go through one example in a second. But this concept of Nash equilibrium and calculating Nash equilibria for games that are relevant in real life actually hasn't really, at least based on my research, hasn't happened yet. So I actually think that this paper at this moment has no real world applications, but it might be like the bridge that allows this concept to be used more commonly in the real world. And so let's start off by talking about what a normal form game is, and then what a Nash equilibria is. The normal form game, we don't have to read all this Wikipedia text, is basically a game where you can describe the entire game in a table. With 2 players, it's a table. With 3 players, it's like a tensor. Well, 3 or more players, it's a tensor. With 1 player, it's a vector. So like if this table here was 3 players, then you'd have like an additional dimension. And the way that it works is that each row, so each dimension describes, actually, I don't know if it's dimension. Maybe it's called rank because we're talking about tensors too. But anyway, like the rows here describe a complete strategy for a player. Each one describes a complete strategy for player 1. So the moves that the player could do would be like top or bottom. But you could actually describe chess, for example, as a normal form game. And then each row would be a possible set of moves that the player could perform for every possible move of the other player. So like that table would be finite but massive, for example, maybe like an unimaginably large number of rows.
Sorry to interrupt. Is chess actually a good example? Because in chess, you play in sequence. You see what the other person did, and then you react to it. Whereas you would almost think that these forms sort of mean you don't know what the other one is doing, so you essentially you make your decisions at the same time.
Yeah, so that's a good point, Arvid. So there's another representation of a game called a extensible. It's up here, extensive form. And in that one, you can model that that you take turns and that you can take into account your current information. But with normal form games, it all has to be spelled out in the strategy in that row. So these are actually like the point is that you can actually represent chess as in normal form, but it's probably going to be like incredibly hard, whereas it's a lot easier to represent in extensive form.
Gotcha.
Yeah.
So in chess, you wouldn't necessarily know the values of the payoffs because they are learned themselves.
Well, you would, because it's a, you would say like one player would get 1 if they win, -1 if they lose, and 0 if they draw. And the strategy would have to describe exactly how to play in every situation until the finish of the game.
Gotcha.
Yeah, so it's like you can represent the entire game in normal form. You can represent the entire game as a table, or tensor. And the way it works is that like each row or column, or when we're going to 3 dimensions, is a strategy that completely describes how the player will play in the game. And then the cells within the table are the payoffs for each player. So this is just so for example, if player 1 played the move top, and then player 2 played left, then player 1 would get would get 4 points, and then player 2 would get 3 points. That's an example. One example, an interesting example of a normal form game is called the prisoner's dilemma. It's one that comes up a lot, and so in this article here, they even talk about how you can find a lot of different places in our world where, like in the economy, where it comes up. But the basic idea is quite simple. It's so you have the prisoner's dilemma is described as follows: like, so you have 2 people who have robbed a bank, and they've been caught by the police. And if both of them say nothing, they both spend a year in prison. If both of them say, if one of them defects and the other doesn't, then the one who defects spends no time in prison, and then the other one who defects spends 5 years. Who doesn't defect spends 5 years in prison. And then if they both defect, then they both spend 3 years in prison. And if your total utility is like the negative of the number of years that you spend in prison, then the worst outcome is actually that they both defect. But if you look at the rewards, the person always has an incentive to defect. So, for example, say neither of them defect, and Elizabeth is like, well, if I do defect, then, and the other person, and Henry doesn't, then I have an incentive. I should defect because then I spend 1 less year in prison. I spend no time in prison. But say that Elizabeth is in a situation where Henry defects, she would be spending 5 years in prison. So in fact, the best thing for her to do is also defect, so she spends 3. So no matter what situation you're in, it's always in your interest to defect. And this kind of brings on, can kind of, this simple example describes kind of the idea of a Nash equilibrium, where the Nash equilibrium of this case is that they both defect. And that's because if, oh, yeah, go ahead, Damien.
I was just wondering, why is it called an equilibrium?
It's because, so the reason why it's called an equilibrium is because it's a very specific kind of equilibrium, which is that it's in no one's interest to change their strategy if no one else changes their strategy. So, for example, let's take this. Like I told you that the Nash equilibrium of this game is for both of them to defect. So say that Henry is thinking about changing his move. And so a unilateral change would be only he changes and Elizabeth doesn't change. So instead of defecting, Henry decides to cooperate with Elizabeth. Instead of getting 3 years, he'll get 5. So it's not in his interest to change his move from where it is because he would just get a worse payoff. And the same is true of Elizabeth. The same of that, but that isn't true when they both cooperate. So if they both cooperate, they both get 1 year. But if Henry doesn't cooperate, I mean, if Henry cooperates and then Elizabeth decides to change, she gets 0 years. So it's actually in her interest to make that move, assuming that Henry doesn't change his strategy. So that's what defines a Nash equilibrium. It's one where the payoff that you get is the best or equal to, like, either the best or equal to, greater than equal to the best payoff you can get if no one else changes their strategy and you change your strategy. Yeah?
I think that sort of actually features into this particular paper, right? The equilibrium is like a fixed point where you have some dynamic optimization where you try to improve your payoff, and everyone does it in parallel, and it sort of converges to a point, which is, of course, what the paper itself trying to do. So, yeah.
But I think a lot of the math in this paper actually relies on the fact that it's a Nash equilibrium, because you calculate your gradient with respect to like everything else staying the same except for your strategy.
Yeah. And of course the utility function being linear.
Yeah, sure. So that was like a quick introduction into Nash normal form games and Nash equilibrium.
I have a quick question.
Go ahead.
So if game is repeated only once, it makes sense both to like betray another person, but if it's repeated multiple times, it's like infinite, it's better to like keep this like 1-1 case, right? And like, what is changing?
Yeah, go ahead, Julian. Or Arvid. Or Julian first, because you raised this one first. Or Arvid, if Julian doesn't want to say anything.
There is this a theorem, or I think it's experimental rather than actually proven, that of course when you do it over and over again, you sort of keep a track record of what your opponent did in that situation, and that of course changes how you would change your policy yourself. So it's probably that's kind of gonna get missed, right? Your strategies can be probabilistic and very often are, right? Think of rock paper scissors.
Yeah.
A clear strategy would be always go scissors, which eventually the other person would figure out and would always go rock. And the Nash equilibrium there would be a third. So you do a third randomly, because everything else, someone would be able to exploit and get out. And but in repeated games, because you get that history, there's a very nice solution or answer. It's called the tit for tat strategy. I think that if
that's right.
If you both cooperate, then just keep on doing what you're doing. If one person defects once, if you defect once, essentially in retaliation, and then go back to your optimal strategy, if everyone is doing this, it also becomes stable in the long run. But I don't think it's proven. It's more like it. Yeah, please.
Can I interject, because this was the work that was really underpinning the work of Robert Axelrod from the 80s. He published a famous book in 1984 called The Evolution of Cooperation. And what he shows is, you're right, the tit-for-tat model in general beats everything else. He had programmers and professors and ordinary people from all around the world do hundreds, indeed thousands of iterations of this. And basically nothing beats the tit-for-tat except for tit-for-two-tats. But it only works when everybody's being nice. I mean, this work is actually, I know it sounds crazy, the key to human future survival. It is so important, this cooperation stuff. So yeah, absolutely right. If you only do one game, it pays to defect, exactly as you said. If you do multiple games, as I put in the comment there, the key is it's either multiple games or you mustn't know what the end is. As soon as people know when the end game is, like when they ran it the first round, everybody knew as 200 games. So the models started trying to defect towards the end, and that always lowered the reward. By the way, in the Axelrod version, it was all positive. People would get rewards rather than the negative one with the prisoner's dilemma. But it's absolutely the same thing. So they found that the key was to play nice, always start by not defecting, but it was absolutely key to retaliate quickly and hard, but then be forgiving. So these are all, and so yeah, that's this paper is potentially very interesting for looking into this.
Yeah, I think Julian points to why this is actually this is interesting and important work, because of all of these different types of examples that we have of how normal games can tell us, or how finding Nash equilibrium can tell us how to act optimally. But we just don't have the techniques yet to really do that for like more complicated games, which hopefully segues me in nicely to kind of describe the problem, and then also like the reason why this work exists, which is the problem within the problem. So I'll give like a quick but hopefully understandable explanation of a normal form game as they define it here, which is that you have n players, which each independently choose n possibly mixed strategies. So each player has its own strategy. And a mixed strategy is one where when you choose, like say you're going to play the game, you have multiple different options on how you could play, multiple different moves you could make. You could defect, you could cooperate. And a mixed strategy is one where instead of choosing one of those to do every time, you randomly sample from a probability distribution over those actions and choose the one that's sampled and perform the one that is sampled. So it's one where you could possibly one time do one strategy and possibly one time do another. And it's easy to, especially in like a two-player game, to come up with payoff functions where the optimal strategy is mixed. Like, so the Nash equilibrium strategy is mixed. I shouldn't say optimal. And so, yeah, each player chooses a possibly mixed strategy. And it's a Nash equilibrium when no player has any incentive to unilaterally deviate from their strategy, which means that everyone else's strategy is the same. If you change yours, you're going to either earn the same payoff or one that's worse. We've talked a little bit about why they're useful. Now here comes the reason why this paper is written, which is that, as I say here, when considering Nash equilibrium beyond the two-player zero-sum scenario, where a zero-sum game is one where like the total utility, if you sum it up, that's given to each player equals 0. Some examples are like in chess, the way that they reward people for games and competitions is you get 1 point. Actually, it's not zero-sum, because if you oh, you know, it's one sum of 1, or no, it is it? Sorry, I'm just thinking, because in chess you get 1 point if you win, the other player gets 0. So the sum is 1, not 0. But a zero-sum game would be one where, like in chess, if you tie, you get no points. If you win, you get 1 point, and if you lose, you get -1 point, because the sum of the outcomes will always be 0. The most classic example for me of zero-sum games is actually like investing, because if one person wins, then another person loses. That's just how it works. But so outside of these zero-sum games with two players, it's actually quite hard to come up with Nash equilibriums. First, because it says how n independent players would collectively identify a Nash equilibrium when multiple equilibria are possible is difficult. And then approximating even a single Nash equilibrium is known to be computationally intractable. So basically, overall, the computation required to find a solution or a Nash equilibrium in more than very simple games is NP hard. That's what they say here. And that's what this paper is about. How do we come up with a method where we can start to find Nash equilibrium for more complicated games? So that we can start applying all of these really cool ideas to more complex scenarios that are probably more approximate of real life. And the one thing that they point out, which I think is interesting, I think there's some commentary in here, is they say, like, from a machine learning practitioner's perspective, such computational complexity computational complexity results hardly give pause for thought, as collectively we have become all too familiar with the unreasonable effectiveness of heuristics in circumventing such obstacles. And an example of a heuristic for them is using stochastic gradient descent to optimize neural networks, because stochastic gradient descent only guarantees that you'll get to a local, well, doesn't even, in the limit, it guarantees that you'll get to a local minima. And so they're like, well, if you do machine learning, you're used to dealing with like billions of parameters and using these heuristics like stochastic gradient descent to get good results. But finding Nash equilibrium is different than that. That it's in fact a harder problem, where then that's why we can't just like naively apply the same techniques. And they give some examples, like on a 4-player Blotto game, we found only a brute force pure Nash equilibrium enumeration is able to return any Nash equilibrium within a 1-hour limit with the given techniques that are available. So yeah. Sorry, I'm just reading this next point. This is the main point that they say. More to the point, any computational technique that presumes exact computation of the expectation of this tensor sampled according to X similarly does not have any hope of scaling beyond small instances. So what you'll see is that in the case of mixed strategies, you're trying to calculate like the expected utility of the set of mixed strategies. And their point is that like calculating this in larger games is just really hard. And it's hard for 2 reasons, which I think they say on the next page. Okay, well, they don't. But so it's hard for 2 reasons. It's hard because usually like the utility function that you're optimizing is composed of like nonlinear complex functions. And consequently, like simple Monte Carlo over that leads to a biased estimate of the expectation, where a biased estimate means that as you get more samples, you don't converge on the true value, you converge on a different value. And consequently, you can't use those results in order to find a Nash equilibrium because you're not calculating the utility correctly. So what do they do here? They just say, can we solve via unbiased stochastic gradient descent? I won't go into that much detail here. Yeah, let's just, maybe I'll give like an overview of what they do. So what they do is they take a Nash equilibrium and they define a loss function. And they show that if you minimize this loss function such that it's at 0, then you are able to find a Nash equilibrium. And then there's some, we'll get into this in a second. And then there's some, they have to do something, they have to add something to the loss function because the loss doesn't behave well on the boundaries of the optimization landscape. And so they add that in, and then they can give you some like theoretical guarantees, even like in terms of convergence rate of the answer, about like finding approximate Nash equilibriums using their method, where you use that loss function and you use an out-of-the-box stochastic optimizer in order to find the Nash equilibrium. And then they do some experiments, which I actually don't think we're going to go into because they're not in the paper, they're in the appendix, which show that like using their loss function and stochastic gradient descent, they're actually able to get like state-of-the-art results in quite a few benchmark games. Okay, so there. Let's see. What do I want to? Okay, so let's do some more definition. So we said before, there's a lot of definition here. So I hope that I can explain as little of it as possible and still make this paper understandable to you guys. So we said there's n players, and each player will have like a certain number of strategies they can choose from in the game, which is mk, where k is like the number of the player. So if there's 2 players, there's going to be player 1 and player 2. M1 would be the number of strategies, pure strategies, which is just like a single type of move, a type like single action you can perform in the game. And then each player also has a utility function, which is it's over here. Pi is more like concatenation than product. They use that notation throughout this big pi throughout the paper, by the way. But so basically, you know all the actions that were played in the game, and you get a payoff between 0 and 1. That's how the utility function works here. Yep, I hope that makes sense. So you only know your utility after the game is played. I don't actually think.
Isn't that
Yeah?
Because K here is the size of the player's action.
No, K is the player. So K. So this is like the utility function of player K, which is from 1 to n.
Yeah.
And then AK is the strategy, like the pure strategy chosen by each player for all K players. And so once you know that, you get a utility out.
Yeah.
And so player K may play a mixed strategy by sampling from a distribution over their pure strategy. So that's like, as we said before, where you might have multiple different actions you can perform, and the way that you choose is by sampling from a distribution over the actions, and you just choose the one that you sample. That's a mixed strategy. But it adds like an additional level of complexity, but also is kind of what makes this whole thing work. Which is like they say, let player K's mixed strategy be represented by a vector xk, where it's on like, I forget what the name of the symbol is, but I'll just say big delta, where this is the, yeah, go ahead, Arvin.
I think that is the simplex, but it's
Yeah.
If you think about it, if you have, say, 2 options to play, but it just means that the sum of probabilities has to be 1.
Yeah.
Meaning that in 2 dimension it's the diagonal of a square. In 3 dimension it would be the diagonal cut of a cube. So that's I found it quite complicated as you described it, because at some point they say, oh yeah, the tangent space is always the same, but of course, because the cut in a cube doesn't swivel around, right? It's a straight cut, and that's why this problem is actually not nonlinear as they. I'm not quite sure what actually connection with the nonlinearity in the beginning was versus here, because here, as you pointed out, right, in the UK, it's the sum of linear terms essentially.
Yeah, it's a good point. Let's see if we can figure that out as we go along. But so the probability vector is on the, like as Arvid pointed out, if there's 3 different actions, then it will be a 2-dimensional vector on like the 2-dimensional probability simplex. And I just wanted to show you guys what a simplex looks like. But Damien, do you have a question?
I was just going to ask why do they refer to it as a mixed strategy from the pure strategies?
So a mixed strategy is one. It's because you have the possibility of playing doing more than one action. So it's a mix of pure strategies essentially. A pure strategy is you can only perform one action. A mixed strategy is that you could perform more than one action, and it's based on like a probability distribution that you create.
Okay.
So this is what like a 3-dimensional simplex looks like. So this could be used, probability simplex. So this could be used to model a probability over 4 actions. And like the extremes are of this volume are 1, like 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, and 0, 1, 0. So like these corner bits points are pure strategies, and the interior of it is mixed strategies. And you can be anywhere within that volume and describe a valid probability distribution, because as Arvid said, there's like a 4th probability that will absorb the rest of the mass. But this is what the simplex looks like, which is, I'm showing it because I hope it will make it more obvious, will make parts of this obvious later, but like of the paper more obvious later.
So what was the 4th probability there? This was just 3 actions, no?
Yeah. No, but as you pointed out, the simplex, like a probability distribution over 4 actions would actually be like a hypersphere in 4 dimensions, and you have to be on that surface.
It would be
But instead, they just show it as they do the 3-dimensional simplex, and then they calculate the 4th probability distribution.
I was going to ask, is no action also a valid outcome of this?
No, I think you have to choose an action, because unless no action is an action,
Right.
you have to play the game. So yeah, a mixed strategy is described as like a vector it's a vector with mk minus 1 values, where mk is the number of pure strategies, and it's actually representing a vector that sums to 1. And then, okay, each utility is then extended to this domain so that, okay, and so this is how you would calculate the utility with a mixed strategy. I won't go too far into that. They define Nash equilibrium as where so ZK is your strategy if you change it. Sorry, I'm going a little bit too fast. As we said before, like each player will play some mixed strategy, and so player 1's mixed strategy is this x1, and all of them together are this like boldface x. But you can describe all of the other players' mixed strategies except for yours as x minus k. So, for example, I'm just describing notation here. Xk, if you had like parentheses xk and then comma x minus k, that would describe boldface x, the whole thing. Because x minus k is saying x1, x2, up to xk minus 1, and then xk plus 1 to xn. So for example, over here, what this is saying is like the utility that you would get from changing your strategy from xk to zk is less than whatever it was when it was your utility was when it was xk. That's what a Nash equilibrium is. And then they say like sometimes people talk about like relax Nash equilibrium to be like an epsilon Nash equilibrium where you have some buffer. So you don't have to be you don't have to be the exact perfect. You're always greater than or equal to all other utilities, but you can be within some ball of those utilities. We don't have to worry about that. This does come up, but I don't think we're going to even get into it, like about these bi-matrix game approximations, because it's going to get too complicated. Okay. The next concept that I wanted to introduce, and the reason why I talked about the simplex. So they define something which they call a projection vector, or like they have a projection operation, which is what they're showing here. That's what all this notation means over here. So it's like a function that takes a vector and projects it onto, like like calculates the tangent of that vector on some surface. So for example, let's see if I can draw. I think I can draw. No, I can't draw. No, I can't. Anyway, so the reason why that's important is because you can only optimize your strategy. Like you can only change your strategy from points on here, like within this simplex. And so you always want to, and in higher dimensions as well. And that's actually what's called like a manifold, because it describes like only a part of the like the entire space that you that these strategies could be in. Because like these strategies are all like we said, mk minus 1 dimensional, but you can't have any value. MK can't be like these strategies can't have any value like because they have to sum to 1. So for example, you couldn't have a strategy that was like 100, 0, 0, because that vector doesn't sum to 1. And that's what defines like a manifold or a surface on which you have to optimize things. So really, whenever you calculate the utility and you want to figure out like how good it is, you actually have to project it onto that surface in order to figure out like if you could improve the utility at all by moving around on that surface. And that's what this operation is doing. This big notation is saying like, yeah, go ahead, Arvid.
Yeah, I found it quite helpful to think about it from the optimization point of view when you are already say you have a point and you calculate the gradients, right? So you do your gradient update step, and if you just take a very generic update step, you're gonna, as you rightly pointed out, move away from that manifold, right? And but because the update step because it's like a quadratic form, right? So you just multiply by that projection, and it sort of just means that the sum of the gradient terms become 0, right? So that your total probability doesn't get moved about. So it's I almost think you probably started from that thing and then worked their way backwards into such a loss function by just squaring it, and then after the fact showing that it still works when you don't know the exact function. I think what I found quite helpful to understand is that you have to sort of know the gradient, right? So that is where I say their form is very, very unhelpful. You know, this gradient sign, which is actually should be gradient of u, right? That is the thing that you fundamentally don't know. Where in many games where they say if you have a lot of players and you have a lot of different actions, you don't know what this inverted triangle, aka the gradient, is, right? And I think their contribution was to show that even if you don't know that and you can only approximate it, but you can approximate it unbiasedly, then this whole thing still sort of pushes you in the right equilibrium state.
Yeah, I agree. But you've also pointed out something I forgot to explain, because I didn't explain that. So the gradient of the utility function of player K's utility function with respect to their own strategy is denoted by this. And that vector is pointing in like any direction you could think of. And that's why you need to, where Arvid explained it a lot better than I did, you actually need to project it onto the tangent space of this simplex in order to make sure that you're moving, like you move. Well, not only that you're moving in the right direction when you're optimizing, but like so you can check if you're at an optimal point. And we'll talk about that in a second. Like what do I mean by that? But yeah, so hopefully we'll go over it again, but hopefully some of that made sense. They talk a little bit about like why the other methods that are around for optimizing for Nash equilibrium don't work. They say it over here. A random variable appears as an argument of complex nonlinear functions. And what that means is that you get biased estimates under sampling, and you need to do sampling to estimate these gradients. or it's unclear how to sample. So maybe you have a method which is unbiased, but they don't know how you would actually use it in a practical sense. That's what they say over here. And those are the two key challenges that this paper addresses. As you say, you go ahead, Damien.
There's a question in the chat. I can read out if you want. So in this framing, are the realized utilities just the rewards in the payoff matrix, or are the rewards subsequently run through unique payoff functions per agent as well?
They are. It's the former. So the payoff matrix describes completely the payoff for each player, based on their strategy, or based on not based on their strategy, but in a mixed case, because they might have a mixed strategy, but based on like the sampled action that they get based on their strategy. Okay. So Nash equilibrium as stochastic optimization. Let's see how we're doing on time. We're doing okay. Trying to figure out where I want to get to in 15 minutes. Okay, let's see where we get. So this first lemma, I think, is the one that's like important to to the most important to understanding, like conceptually, or what they're doing here. They're saying assuming player K's utility is concave in its own strategy, which is just like it's a function. It's a way that a function looks that makes it concave. I actually just showed you a convex, but anyway. So assuming that the function looks a certain way, a strategy in the interior of this in simplex is a best response if and only if it has a zero projected gradient norm. So a best response you can think of as like, it's not a Nash equilibrium, because a Nash equilibrium actually would require that all of the players have a best response, but it's saying one player's strategy is a best response if there's a zero projected gradient norm. And that actually makes a lot of sense if you think about it, because what it's saying is like, okay, you calculate the utility, and then the utility is this some function, like what you can think of as a Lofts landscape, like with peaks and troughs. But the thing is that it's not like the normal optimization that we do where we can go anywhere in terms of our parameters. We have to stay within the simplex. So we have to calculate the gradient of that utility, but then project it onto the simplex, the tangent space of the simplex. And if that projection is zero, that means that we are in a best response, or like a local optima. So that's kind of the main idea. It's like, instead of what we're used to, where you calculate your gradient, and if it's zero, then you're good, then you're in your local minima, and actually zero, and then your second derivative is positive. But anyway, in this case, you actually have to, you might already be in a local minimum and you don't know it, because you have to project the gradient onto the simplex, and then it has to be zero. And everything else like follows from this in terms of the intuition, in my opinion. Okay. Yeah, go ahead, Arvin.
I was wondering, is it actually fantastically different from a regular constraint optimization? Say provided you actually knew the matrix completely, right? So you know all the possible ways players can play. That would be just a standard constraint optimization, no?
I feel like maybe constraint optimization is a generalization of this problem, and this is one approach you could take.
Yeah.
Maybe. Like, I wonder if you could use Lagrange multipliers to enforce the
I would have thought
simplex.
You should get pretty much exactly the same thing, right? If you know all the coefficients, then that should be how a Lagrange multiplier to that problem looks like, no?
Mm-hmm.
Yeah. Sorry.
Okay. So the next I'll just tell you what the next thing they introduce is this idea of exploitability. I'm cognizant of time, so I don't want to go to. So, but this is actually an important concept, which I feel like they don't explain. But what exploitability is like basically how much better your you could think of it as like how much better you could be than how much you can improve your strategy is the exploitability. And so like if you have an exploitability of 0, then you can't improve your strategy and you're at a Nash equilibrium. Actually, I found a definition which I thought was good, but then I got rid of it. Let's see. So exploitability measures how well a strategy profile approximates a Nash equilibrium. Yeah. The closer it is to 0, the closer the policy is to optimal. So because they talk a lot about exploitability, and they provide bounds for exploitability because they're saying that like using this loss function, you can upper bound exploitability. So if you minimize this loss function, then you are minimizing exploitability, which means you're getting closer to a Nash equilibrium. That's why they introduced this concept of exploitability here, which I actually don't think is very clear that that's the case. That's why they're doing all of this. But anyway, so we've gotten to the point where we've defined a loss that if you can minimize it, then you can find a Nash equilibrium. And that loss is this loss here. Oh, sorry, this loss up here. Where it's like you take the projected gradient of each of the utility functions squared, and you sum them. And it makes sense, as we talked about before. If all of them are 0, then all of the strategies of all the players are best responses, which means it's a Nash equilibrium. We've shown exploitability, but the thing is that estimating this loss is actually difficult because you have to take an expectation because the strategies are all mixed strategies. But it's also important that they're mixed strategies because I don't think that the math would work out if you were only I think you'd have to do pure enumeration if they were just looking at pure strategies. And also a lot of normal form games, the optimal strategies are mixed strategies. But so you have to perform an expectation, which is what they're talking about here. But the problem is that the expectation is probably is like, if you don't do it correctly, is going to be biased. So how do you estimate this loss in an unbiased way? And they talk about it a little bit here, but I'm going to keep going. But the key to it, as Arvid said before, is calculating an unbiased estimate of the gradient. This thing here. If you can do that, then you can calculate this loss function, and you can use it to optimize the model. And they talk about over here like different ways of doing it, because basically what you have to do to calculate the expectation exactly is enumerate all possible outcomes given people's strategies. But that's way too computationally complex. So they suggested a couple of other ways. One would be that you just like sample a single action from each other person's strategy, and then you enumerate all of yours, or you enumerate all of theirs and you just keep yours fixed. There's a couple ones here. You go ahead, Arvid.
Yeah, I was wondering, right? Because the general form is like you have these coefficients that you don't know times all the other times the product of the probabilities that a player plays that because there is no connection between those coefficients, right? They could in principle be anything.
Mm-hmm.
I think that the theorem essentially is just saying that if you sample randomly, you're not guaranteed to find the best solution, right? Because you would have to sample approximately all the number of combinations times until you find the right one, just because there is no connection between all of them, right? So they could be, you could find suddenly one coefficient that is the best for everyone, and suddenly your gradient estimate might change completely from one step to the other. So that is where I got a bit confused, or how can we interpret these results, right?
Well, you're not sampling coefficients, you're sampling actions.
Yes, but say if your utility is action based, right? So when you sample
Mm-hmm.
one set of actions, you essentially measure exactly what is the payout functions for each player, given every other player. So actually, sorry, for every time you sample, you get k of those coefficients, right? So, but those coefficients could say if only one of those players changes their action to another action, you get a completely different set of coefficients that potentially are very, very different looking, right?
I see. Yeah.
And I think that is where the probabilistic nature comes from. That essentially, I think they're saying, I haven't quite understood it, that if you sample long enough, you should at least get a majority of those coefficients sort of sampled out, which then means that your gradient approximation is probably just as good as if you were to know all of the coefficients in the first place, I guess. But that part I didn't quite understand.
Yeah. I'm not sure either, to be honest.
No worries.
The thing I was more confused about was because they labeled the two gradient estimates as 1 and 2. I was like, do you have to estimate your gradient twice? I think you do, based on the math that we're showing up here, but that's not super clear.
I think that wasn't for the Hessian calculation, where essentially because your opponent also does the same thing, and so never mind. I think that's
I think you have to do it twice, because if you don't, then you're not gonna it's because of what they're showing here. If you just use the same if you use the same estimate for both of these two parentheses, then you end up not correctly calculating the the square. But if you estimate the gradient twice, then they're identically distributed but independent.
Yeah.
And you can get the correct you can do the computation correctly.
Yeah.
Okay. There's one last thing I want to say. Hopefully, let's do it quickly. So all of the cool math that we've talked about and what we've shown you is only works if the equilibrium is within the simplex. So it has to be within this volume. It can't be on the boundaries. And everything blows up if that happens, based on what they've said. And consequently, they modify their loss function so that you're guaranteed that in this new game with this new loss function, all the equilibrium are within the interior. So all of their math works. And what they do, the way they do that is that they add entropy as a term in the utility function with some kind of coefficient to balance entropy versus the actual utility. Basically what that does is it makes it such that you can guarantee that your optimization is never going to blow up or act weird, but at the same time you can still get pretty close to Nash equilibriums. There's actually I think the best way to show it is through a diagram that they have. Come on, go to the next page. There we go. Okay. If I zoom in here. Sorry, guys, my computer is glitching a bit. So the black line is exploitability. And so you can see when it gets to its lowest point, these are Nash equilibrium. And then using their loss function is an approximation for it. So the red is their loss function without the entropy. And then the blue is their loss function with the entropy. And you can see that in this game that they show here, the entropy shifts the equilibrium a little bit from where the Nash equilibrium actually is, but it's close. And so that's their whole point, that and you can make it closer by making tau smaller. And so that's how they keep everything kind of nice, but still they allow you to find approximate Nash equilibriums. So that's what the impact of adding this entropy term is in a visualization. And so we didn't even cover this section, but I think that's fine. Last but not least is, so through all of this, they've shown how you can optimize to find a Nash equilibrium using stochastic optimization. And it's stochastic because you have to sample to estimate the gradients of the utility functions because you're using mixed strategies. And then they say, like, because of that, now we can use stochastic gradient descent, or they also suggest this X-armed bandit method to do the optimization. And the cool thing about the X-armed bandit method is it actually finds a global optima within a certain, and there's like convergence guarantees and everything for that. So that now they've shown how they can find, for example, a global optimum within a reasonable, with a convergence rate guarantee on it for normal form games. And how am I doing? Okay, boom. So that's the paper. Sorry for the whistle stop tour at the end. But I hope you guys learned something from it. And I do think it's a really cool paper. A little bit hard for me to understand, but hopefully if I read it a couple more times, I'll understand it better. Yeah.
Thank you very much. I found just rewriting it in terms of simpler symbols helps. Like having rather than using the nabla, just write gradient of u with respect to x, and suddenly I think it might be mean, but I think they might have done it because if you plug it in, it looks actually very similar to one of the losses that was suggested, I think, in one of the other papers. So maybe to make it look slightly more novel, they make more stuff. I mean, some of the, because also they double use indices like k for player, but also then k as an index for the action. And then at some point they use this tensor notation where actually having this double index means something different, and that is just bad. That is just yeah, there's
a lot of abusive notation for sure.
Yeah, but abuse is a nice word. but really interesting paper, and I think quite useful as well.
Yeah, who knows? It would be really cool if this ends up being like a test of time paper and we start doing a lot more stuff with Nash equilibrium now. Yeah. Let's see. Well, thanks everyone for coming. And hopefully we'll see you here next week.
Thank you very much.
Bye.
Bye.
Thanks.